So what we have in this example is a random variable, and it can only be equal to 0 or 1. And here is its cumulative distribution function. So this is k, and this is f of k, the cumulative distribution function, which is the probability that y is smaller or equal to k. So for any k, so probability that is probability that y is smaller than 0 is 0, and probability that y is smaller than 1 is 1. So, and we know that it can only be equal to 0 or 1. Now the question is, can this random variable be equal to 0? Or what is the probability that y is equal to 0? What is that? Well, we know that the probability that y is smaller or equal to 0 is 0, or in words, yes, somebody answered 0, that's right. In words, this random variable is never smaller or equal to 0. In particular, it is never equal to 0, meaning that, yes, this probability is 0. The probability that is equal to 0 is 0. What is the probability that this random variable is equal to 1? What can we infer from this equation, from the value of the cumulative distribution function of this variable at 1? Yes, the probability that this random variable is smaller or equal to 1 is 100%. Meaning, and we know that it can only be 0 or 1. It can be nothing in between. You know, it's a discrete random variable, so it can only equal to 1. So all in all, this is not a very interesting random variable. It's not very random. Well, this variable is always equal to 1. Okay, but that's the simplest or a simplest example of cumulative distribution function and the random variable. So here is a somewhat more involved example of a cumulative distribution function. So the random variable y can be equal to various numbers, again, still discrete, 0, 1, 2, 3, 4, and so on. And we have here given the probabilities that, that it is smaller than certain values. Sorry, to move this out. So this is the cumulative distribution function telling us the probabilities that the random variable is smaller or equal to a certain number. And from here, let's try to understand what is the probability mass function for this random variable. So for instance, what is the probability that this random variable y is equal to 0? Now we're talking about this random variable. What is that? And again, we assume that y can only be equal to 0, 1, 2, and so on. No fractions. Yes. So the probability that this random variable is equal to 0 is 0. Why? Again, we look here, just as we had here. If we know in simple language from here that this random variable is never smaller or equal to 0, then in particular we know that it is never equal to 0. Or in other words, the probability that this random variable is equal to 0 is equal to 0. Okay? So this is the same as here. What is the probability that this random variable is equal to 1? So we look here at the cumulative distribution function. Yes, the answer is 1/6. Why? Well, we know that with probability 1/6, this random variable is at most 1. So if we look at 0 and 1, with probability 0, it is 0, but with probability 1/6, it is 1 or smaller. So with probability 1/6, it is somewhere in here between 0 and 1. But it cannot be anything strictly between 0 and 1. So with probability 1/6, it has to be equal to 1. Or if you want to write this as a formula, the probability that this random variable is equal to 1, this is the difference between the probability that it is smaller or equal to 1 minus the probability that it is smaller or equal to 0, which in our case is, yes, is equal to 1/6. This difference is equal to 1/6. So going the other way, if you have the probability mass function for a random variable that tells you, well, with certain probability, so this would be PMF of x, with certain probability, this random variable is equal, I don't know, to 1, with certain probability is equal to 2, with certain probability is equal to 3. If you want to know what is the probability for this random variable to be smaller than 2, well, you look at the probability that it is smaller, that it is 1, and the probability that it is 2. So now let's call this random variable y. The probability that y is at most 2 is the probability that y is equal to 1 plus probability that y is equal to 2. Let's say the probability that it is equal to 0 is 0. Okay, so the event that the random variable is at most 2, this event is equivalent to it being equal to 2 or equal to 1. At most 2 means you're to the left of this line or on the line, meaning that you're at 2 or at 1. So this is the reason why the cumulative distribution function is called cumulative. As its argument goes to the right, as the argument increases, you accumulate more and more of the mass, more and more of the probability mass function. So returning to this question, when we go back, trying to understand the probability mass function from the cumulative distribution function, we should look at the difference between two consecutive values of the argument and ask ourselves, well, the probability of being at most 2 has grown in comparison to the probability of being at most 1. Why did it grow? Well, exactly because certain probability mass for this random variable is concentrated at 2. And what is that mass that is concentrated at 2? Well, it's the probability of being at most 2 minus the probability of being at most 1. So the growth from this to this is exactly due to this, to the probability of y being equal to 2. So in particular, in this example, probability of y being equal to 2 is equal to 1/6, because that's the difference between 1/3 and 1/6. Okay, a couple of more steps. What is the probability that this random variable is equal to 3? Maybe you can give me the answer already now. Again, look here, look at the cumulative distribution function. So the probability of being smaller than 3 is the same as the probability of being smaller than 2. It means that this random variable didn't gain anything from going between 2 and 3. Or if you still want to use the general formula, then yes, the probability of being equal to 3 is equal to probability of being at most 3 minus the probability of being at most 2. And since for this random variable, both of these probabilities are equal, to 1/3, whatever, there was no growth in the cumulative distribution function when going between 2 and 3, meaning that there was no mass concentrated on 3. So this is really the probability of being equal to 3 is equal to 0. Okay, 2 more or whatever more steps. What is the probability of being equal to 4? Well, again, you look here. By how much the cumulative distribution function has grown when going from 3 to 4? Well, it's the difference between this and this, which is 1/3. So that's correct. It's 1/3. Yes, you answered in the chat. Probability of this random variable being equal to 5, what would that be? Again, you look at the growth, by how much this random variable, its distribution function, has grown when going between 4 and 5. Yes, it's 1/3 again. It has grown by 1/3. And probability of this random variable being equal to 6, what is that? Yes, it's 0. Well, look here. This random variable is for sure smaller than 5. The probability of it being smaller or equal than 5 is 1. So probability of it being equal to 6, 7, 8, or anything else, everything else is 0. So this way we went from the cumulative distribution function to the probability mass function. These things. So we can go back and forth between the cumulative distribution function and probability mass function. And the kind of important thing is to understand that cumulative distribution function kind of accumulates the mass up to certain number. So whatever you had before sums up and gives you the value of the cumulative distribution function at a certain number. Okay, so I'm almost done with this kind of crash course in probability. I will give reference to some of the things that you might have seen earlier. Yeah, so here is the answer to this question again. Some animation, which we didn't remove when going to the distance learning. But anyway, so a cumulative distribution function, which shows the probability that your random variable is smaller or equal to a certain value, it starts at 0 at negative infinity, because your random variable cannot be smaller than negative infinity. So the probability that your random variable is smaller than negative infinity is 0. And the probability that your random variable is smaller than plus infinity is 1, because your random variable, it cannot be larger than plus infinity by definition of plus infinity. And in between minus infinity and plus infinity, the cumulative distribution function does not decrease. So if you have two numbers, A and B, and A is smaller than B, then the probability that your random variable is at most A should not exceed the probability that your random variable is at most B, right? Because being smaller than A also means that you are smaller than B. So the probability of being smaller than A is smaller or equal to the probability of being smaller or equal than B. And that's what essentially is said here. So if A is smaller than B, then this is A, maybe this is B. So the probability of being smaller than A cannot exceed the probability of being smaller or equal than A. Sorry, probability of being smaller or equal to B is at least as large as the probability of being smaller or equal than A. So these are some of the properties that any cumulative distribution function has. Interestingly, any function that has these properties is a cumulative distribution function for some random variable. So you can draw an arbitrary function like this, which I did on picture, and that will be a cumulative distribution function for some random variable. So I'm looking at the chat. What if the probability of a smaller number is greater than a larger number? So in terms of the probability mass function, that may happen. So let's go back to probability mass function. For instance, over here, we had, number 4. The probability that y is equal to 4 is larger than probability that y is equal to 1. So the PMF, probability mass function, doesn't have to be. Okay, sorry, you wanted to have an example where the probability of a smaller number is greater than a larger number. So then I took on numbers for my example. So let me take 2 and 3. So the probability mass function, probability of this random variable being equal to 2 is larger than probability that this random variable is equal to 3, because this is 1/6 and this is 0. But so probability mass function, yes, it can go up and down. But if you look at the cumulative distribution function, well, here it is. The probability that this random variable is at most 3, this thing, cannot be smaller than this thing, than the probability that random variable is at most 2. Even though the probability of being equal to 2 is larger than the probability of being equal to 3. So that's the difference between probability mass function, which shows how much you have, how much mass, how much probability you have on any point, and the cumulative distribution function, which shows how for any value, it shows how much probability you have to the left of this line on all these points up to and including this one. So if 3 was smaller, it would be before 2, where if 3 was smaller than 2, you mean? Or if 3 had smaller, if this thing, you probably mean if this value were smaller than this value. No, it could never be smaller. So as the argument of the cumulative distribution function increases, the value of it also increases or doesn't decrease. It never decreases, the value of the function. Because the farther to the right you go, the more mass you have accumulated. So the cumulative distribution function shows the total mass, the total probability, which is kind of to the left of its argument of the value. Yes, PMF may jump up and down, but the cumulative distribution function can only grow or stay the same. I mean, it can also stay the same. Okay, so yes, continuing with distribution functions and probability in general. Right, so when we say that we know a random variable, what we really mean is that we know its distribution. So we cannot know anything more than that, but there is also nothing else to know about random variable. Knowing a random variable means knowing its distribution function. And most often when we speak about distribution function, we mean the cumulative distribution function, because any random variable has a cumulative distribution function. For the discrete random variables, we can have the probability mass functions. For the continuous random variables, we can have the probability distribution functions, the PDF. But PDF doesn't always exist. So, few more functions. Something called the complement cumulative distribution function. So, you know, a random variable can either be at most certain value k, or can be larger than this value. So take any number k, and you know, the sum of the two probabilities of being at most k and being larger than k is equal to 1. Because, you know, you're either smaller than k or larger than k. And if you solve this equation for the probability of y being larger than k, then you get that this probability is 1 minus this probability. So this is really 1 minus the CDF. So this is the CDF, the cumulative distribution function. And sometimes this thing, this difference, has the name complement CDF. So it's the probability that the random variable is larger than certain value. Okay. Lots and lots of functions, right? Especially for random variable stuff. So there is a question. It says that all values should be 100% together. Yes, yes, of course. So the yeah, I think that this question in the chat refers to the previous slide. Yes, so this equation here says that yes, altogether the probability of being most some number plus the probability of being larger than number should be 100%. Okay, so I'll try to switch to sharing the screen from my computer, so I will temporarily stop sharing my tablet and go catch up in the slides in here. Yes, with this. Yes, we were talking about lots and lots of functions, and there is a reason for that. The notion of a function is one of the most important, most basic notions in mathematics. What is the most important notion, or the second most important notion, in addition to the function? That's the notion of a set. So that's even more basic. And I guess you might have seen it in the, well, this mathematical prelims lecture, which I put as lectures 0. Yes, a set, most important math notion. And the second most important mathematical notion is the notion of the function. And in fact, despite the name, a random variable is neither random nor variable. I know it's confusing. Believe me, it's not me who came up with the term random variable, while it being neither random nor variable. But this is a question that I'm asking in the interviews. Anybody who says that he or she has some familiarity with probability, I'm asking, what is a random variable? Is it random? And is it a variable? And that's a tricky question because it's neither random nor variable. Essentially what it is, it's a function. And again, something that you might have seen in your probability course, and maybe this is a picture from a book, and I know the book has changed, but any book, or any good book at least, should mention that the random variable is a function, well, from the event space or state space, whatever you call it, into some values, into numbers, if it's a discrete random variable. It could be other things. I mean, you could have a random variable that appears from tossing a coin, and then, yes, it becomes heads or tails. There could be other random variables, you know, a lot of things, random things can happen in the nature. and then you can have a random variable which represents the temperature or anything else. But in general, a random variable is really a function from the from the state space or event space to, for instance, numbers. So that's one reason why we have so many functions. Few more things about random variables. So we are kind of finishing this crash course in probability, if you wish, trying to give you everything that you may need to deal with the revenue management in this course. So the expectation of the random variable or expected value or mean value or average value, there are various names for the same thing. As I might have joked, there are two problems in modern science. The second one being too many notions for the same thing, too many terms for the same thing. So here again, one example, expectation and mean value, whatever. So it's a number which is defined like this. So you go over all numbers and you multiplying every number by the probability of the random variable being equal to that number. And when you do the summation, that's you get the expected value of the random variable. Hopefully you have seen that. The expectation can be calculated by a formula. Here is a formula. Sorry, I meant to do annotations. Anyway, down here there is a formula for the expectation, and here is the definition. And one last but not least thing is the variance of the random variable. So how random this variable is, how much it varies. So by definition, the expectation of a random variable is, so the variance of the random variable is this. Expected value of the random variable minus its expected value squared. I guess it's harder to say than to see what it is. And here is the formula for the variance. It's basically the difference between square of the expectation and expectation of the square. There is also something called the standard deviation, the sigma, which is the square root of the variance. So these things show how much the random variables vary. Okay. Trying to get out of annotations now. Yes, an example, the same random variable that we had before. What is its expectation? So now I have great expectation of myself. I think that I will be able to quickly switch from sharing my screen on the computer to sharing my screen on the tablet and do the calculations. Let's see. Okay, I have to go further to scroll forward. I think it scrolls too far. Okay, yes, so the expected value of this random variable. So, well, you can calculate it by this formula, or you can go by definition. Expected value of the random variable is the sum over all values. So I'm trying to move out this thing. Annotation, whatever, dashboard. Yes, so yeah, the expected value is the sum over all numbers k, this number times the probability that the random variable is equal to this number. And let's calculate this sum for this random variable. So for k equals 0, we have 0 times the probability that k is equal to 0. I think we shouldn't care too much about that, whatever this probability is, plus 1 times the probability that y is equal to 1. And as we saw, this probability is equal to 1/6, plus 2 times the probability that y is equal to 2. And as we So it's 1/3. Oops, sorry, it's 1/6, because it's the difference between this and this. Plus so on, 3 times the probability of this random variable being equal to 3. And we know that that thing is 0, so we kind of don't care about this line. Plus the probability of, oh, sorry, plus 4 times the probability of this random variable being equal to 4. And the probability that this random variable is equal to 4 is 1/3, because it's the difference between this and this. Plus 5 times the probability, well, no, I'm being loose, you can use P or PR for probability, doesn't matter. The probability that this random variable is equal to 5, which is 1/3, difference between this and this. And plus so on. In principle, we can go up to 7 and 8 and so on, multiplied by the probability that this random variable is equal to 6, 7, 8, and so on. But we know that all these things are equal to 0 because this random variable is at most 5. So we shouldn't take these into account. And well, this is 0 because this is 0. So overall, the expected value is equal to this, which is 1/6, plus this, which is 2 times 1/6, plus this, 4 times 1/3, and this, 5 times 1/3. And whatever this is equal to, that's the answer. 21/6, but that doesn't matter. Anyway, this is how the expected value of a random variable is calculated. You go through all numbers k one by one, multiply that number by the probability that the random variable is equal to that number, and you sum all these products as we did here, one by one. Number times the probability that is equal to this number. Number times the probability, and so on. And then you take the sum. Okay, so that was just a quick example. And let's continue with the lecture. I'm again switching to sharing my screen on the computer. We're getting more and more proficient with this. So here it is. Yeah, so this is the probability mass function that we calculated before, but I also quickly went over it. Shouldn't it be 12/6? No, I think it should be 21/6. I guess I cannot go back to the calculations. So 1/6, 2/3 is 4/6, and then few more. Yeah, it's okay. That's right. It doesn't matter. The final calculation wasn't the point. The point was the way how to calculate it. I guess I will have an answer in the next. Yeah, so there it is. Well, of course, it doesn't prove me right, but still. Indeed, doesn't matter. The important thing is how to calculate, not the final answer. Okay, just so that was an example to finish and get to the summary of the probability notions that you may need in this course. I wanted again to show you a few things which, well, I think they are from your course, but again, I might have gotten it from Mikhail, well, before he changed the book, or maybe didn't show these slides or whatever. Anyway, you might have seen things like this, if not exactly these things. So this probability mass function, here you go. That's exactly the probability of being equal to a certain number. So this gray area shaded here. And then the distribution function, that's our CDF, the cumulative distribution function. So you look at all the mass function, all the probabilities up to and including certain value. So this is the mass, and on the right here you have the cumulative distribution function. Other things, yeah, I mean the expected value with all the different names in different languages. The summation, okay, we do the summation over all numbers times the probability that the random variable is equal to that number. Here, I guess you're going over all values that the random variable may assume. So this is maybe somewhat more general than what we had. So this formula works also for random variables that assume non-integer values. For those, we wouldn't have the i's, but anyway, it's the same thing. You're looking at the values that the random variable may assume, and you're multiplying it by the probability of the random variable getting that value, and then you sum in the whole thing, and that's your expected value. I mean, I'm using the square brackets for the expected value. Well, you can use the parentheses or other things. The notation doesn't matter much. It's what it is that is important. So that's the expected value, expectation. Yeah, the well, standard deviation, which is the square root of the variance. So essentially what you have here under the square root is the variance. Maybe this is closest to what we had, expected value of the square minus square of the expected value. So these things should be at least somewhat familiar to you, hopefully. You don't remember them well, then well, here are some of the links to what you might have seen before. Yeah, other things, again, from summer inclination of your probability and statistics course. Random variable is a function. That's what it is. Certain things happen in the event space, and depending on what happens, you get certain numbers as outputs. So it is a function. Discrete and continuous, yes, distributions are random variable. All these different functions, distribution, whatever they're called, probability mass function in different languages. Yes, the probability is the area, again, different functions, and then expected values and standard deviations. So we also have a quick summary of what you might have seen before. And yes, last but not least, the summary of the things well, that we had in this lecture, and also in the language or in the notation that we had in this lecture is, well, that's what it is. The cumulative distribution function showing the probability of being at most certain number, accumulating the all the mass up to and including this number. Yes, then for continuous random variables, this probability distribution function, which is the derivative of the cumulative distribution function. And yeah, that's what it signifies. The probability of the random variable falling between two values is equal to the integral of the probability density function from one number to the other. For the discrete random variable, the probability mass function, which, yeah, maybe the most natural, the probability that the random variable is equal to a certain number. The complement thing, just 1 minus this, or the probability that the random variable is larger than a certain value. I guess we will use it only once, so I would say this is not the most important thing. This one is the most important. It kind of spawns everything. This one is, well, we'll use it once, but just using its definition. The expected value is super important, and variance is quite important. You have to understand how much the random variable varies, how different it may be. Yes, so there are 5 minutes remaining. I guess I'll make a single click, still staying on this slide, and it will show a few videos or links to a few videos that I certainly don't mean to show over Zoom, and I don't have time, and we don't have to do this. But it's essentially, it's more for fun. So there is this Art Benjamin, a mathematician that juggles with numbers, and you can watch what he does with school students. And then there is a longer thing on Ted. You don't have to watch it all, but just to see who he is. And then there is a little bit of his, well, still Ted, but not performance. It's just a speech at TED, 3 minutes. It really speaks about how important probability is. Just that I personally think he said things better than what I could have said. So at your spare time, or in the remaining whatever couple of minutes of this lecture, you can watch that. But we are more or less finished. I will make a click to see what awaits us. We will go back to seat reservation and use all these things that we went over to solve our seat reservation problem at the next lecture. So I will stop